Understanding electrical hazards. The improper use of a device as a result of inadequate training and lack of experience has led to 10,000 medical device-related patient injuries each year. In this video, we cover the possible electrical hazards, how they can affect the human body, as well as how they can be prevented. First, let's take a look at the physiological effects of electricity. The least harmful effect is the threshold of perception, where the current is just large enough to excite nerve endings in the skin and cause a tingling sensation. Let-go current has a minimum threshold of 6 mA and results in the vigorous stimulation of nerves and muscles with eventual pain and fatigue. Respiratory paralysis, pain and fatigue is experienced at currents of 18 mA to 20 mA. The effects are involuntary contraction of respiratory muscles severe enough to bring about asphyxiation if the current is not interrupted. From 75 to 400 mA, ventricular fibrillation occurs. Rapid, disorganized cardiac rhythm results and heart rate can rise to 300 beats per minute. Sustained myocardial contraction occurs between 1 and 6 ampere. This causes reversible contraction of the entire heart muscle, but causes no irreversible damage when briefly applied. And finally, voltages above 240 volts cause burns and physical injuries. There are two types of shock hazards, macroshock and microshock. Macroshock occurs when an externally applied current passes through the body via contact with the skin. Blood, urine, intravenous solutions, and even baby formulas can conduct enough electricity to cause temporary short circuit if accidentally spilled into normally safe equipment. This is especially hazardous in equipment designed with metal chassis and cabinets that patients and staff may touch. If the equipment is ungrounded, the shorted components between the hot power lead and chassis result in 220 volt potential between the chassis and the grounded object. Consequently, touching the chassis and any grounded object simultaneously results in a macroshock. The second type of shock hazard is microshock. Damage from this is due to an electrical current being delivered directly to the heart, for example, through an intracardiac catheter. Sources of microshock hazards are leakage currents. Most important source of leakage current is that which flows from all conductors in the electric device to the lead wires connected either to the chassis or to the patient. If a low resistance ground wire is available, leakage current flowing to the chassis flows safely to ground. Conductive surfaces. Small potentials between any two conductive surfaces near the patient can cause microshock if contact with the heart by one surface and any other part of the body by another surface is made at the same time. Conductive parts to the heart. Some clinical devices connected to a patient increases the chances of microshock. Protection against shock hazards can be achieved through power distribution and by equipment design. Power distribution offers three methods. A grounding system which provides low resistance ground that protects patients against macro and microshock by keeping all conductive surfaces and receptacle grounds at the same potential. An isolated power distribution system which helps reduce leakage current somewhat, but not below the 10 microampere safe limit. And ground fault circuit interrupters, or GFCI. These disconnect the source of electric power when a ground fault greater than 6 mA occurs. Protection by equipment design entails the following. Reliable grounding for equipment. Reduction of leakage current in chassis of equipment and in patient leads. Double insulated equipment. Primary and secondary insulation between chassis and outer case, plastic knobs with recessed screws. Operation at low voltage, macroshock is avoided. current limiters, restrict current to few microampere. Electrical isolation, use of isolation amplifiers, etc. Isolated heart connections, to isolate, eliminate, or insulate electric connections to the heart, for example in external heart pacemakers. Testing the electrical system for faults is a sure way to minimize shock hazards. The following are tests that are commonly performed. Test of receptacle where proper wiring, adequate line voltage, low ground resistance of 0.2 ohms, and mechanical tension are tested. Tests of the grounding system in patient care areas. Tests of isolated power system. And use of an electrical safety analyzer to test the equipment for proper grounding and harmful leakage currents. Although the physiological effects of electricity range from tingling sensations to electromechanical burns and tissue damage, it's important to keep the patient and other individuals safe from electrical shock hazards. Thank you for watching. Stay safe.